Hello everyone. My name is Luis Salazar. I'm going to present our research towards high-fidelity network emulation of IEC, one of our SCADA systems. This work I did it with Neil Ortiz, Shikin, and my advisor, Alvaro Cardenas. Our motivation is basically because during our research, we tackled a lot of problems facing the IEC 104, and this is one of the most popular SCADA protocols, specifically for power grid. Some of our research is revolving around this kind of CPS systems with power grid systems. Even though this is a fairly popular protocol, there are rather few known open source testbeds that we found that actually support this protocol. And the dissectors and parsers that you can find around to work with IEC 104 are often either incomplete or they use some variations of the standard, and you can not always interpret all of the genuine packets that we found. We have found difficulties analyzing some network captures that we had from industry in collaboration with some companies. So this raised the question to us of how can we actually model these types of systems, and how can we work with the systems in a lab environment, because for obvious reasons you cannot be tampering with the systems as you please. So this raised the question of how to work with this kind of systems, and some of the stuff that piqued our interest was the types of attacks that that were executed in Ukraine, specifically in 2016. That was a troubling attack that generated a bunch of problems in that country, and it was basically a malware that affected these power grid systems. I'm gonna go into that a little bit later. So that's the whole problem. 104, even though it is a fairly popular protocol, has not received a lot of attention in a lot of testbeds and open source software that you can use for research. These testbeds, I mean, if you look at all the testbeds, you use most of the popular protocols, the MP3, the IEC 6150, Modbus, and whatnot. And these protocols are well understood, and there are a lot of tools to use this. You often see testbeds that either simulate this type of devices or actually use the devices themselves, or have a hybrid approach in which you have a mixture of simulated stuff through software and also hardware devices interacting with your simulation. And these scenarios, well, you can have these scenarios in small scale testbeds, but if you want large scale scenarios, usually you have software simulations that grant you the capabilities of simulating large systems. However, you don't have access to the network traffic itself that would be present in a real system. And we wanted to analyze a little bit of that. So we started looking for these systems that can allow you to do this, and sadly we couldn't find as many, and those who did often don't support the 104 protocol, which is what interests us. So because of this, we started developing our own framework. It's a Python-based framework that supports this type of protocol, the IEC 104 protocol for power grid systems. And when we created this framework, we wanted to be able to test it somehow. So we came up with two different scenarios. One was a proof of concept malicious program, a malware that would emulate this attack on Ukraine. The malware itself was dubbed Industroyer. So we took inspiration from that and developed our own flavor of Industroyer, if you will, and tested it against our own framework. Our other contribution is, okay, so we have our own framework, our system working, and we want to actually detect this attack that we are making in the system. So we tackle this problem with a small anomaly detection algorithm, try to figure out through the 104 packets if there is an anomaly in the behavior of our simulated system. We're making this all open source, so you can get it on our GitHub. It's going to be available. This is still a work in progress. We are still going through this, so there are still a lot of bugs here and there, but yeah, we're confident we're going to get a great thing out of this. So as most of you may know, the power grid is basically what gives you the energy from the generation up to the users. And since you have different loads throughout the usage of the power, there has to be a control center that regulates somehow the transmission between the generation of the power up to the users. These are the SCADA systems that control the entire power grid. This control is used by the remote terminal units that make an interface between the SCADA system that the operators use to control the system and the actual electronic devices that are in the substations that change the topology and makes the necessary adjustments to regulate the power consumption and generation and transmission from the users. And these devices execute every command that is sent from the SCADA system, affecting the power grid itself. And here is where the 104 is important. This is the type of traffic that our research is primarily interested in, the traffic between the SCADA and the RTUs. This is the IEC 104. These are the packets that either contain the information from the substations that are being controlled or the commands that the SCADA is giving to the different RTUs. So the SCADA will take the measurements and give the operator the system state, and the operator will issue commands to the SCADA, and the SCADA will send the topology changes via the IEC 104 to the different RTUs. So what is the IEC 104? Why is it that we worry about so much about this? The IEC 104 is a standard protocol that runs over TCP. It's comprised of the application protocol data units, which are the main units of the data packets of the IEC 104. It can be comprised either of the application protocol control information or both the application control protocol information and the application data service unit. It depends on what type of format the packet has at one given time. So you can have three different types of APDUs. One can be the I format, which is basically sensor and control data that is being exchanged between the SCADA and RTU. You can have the S formats, which basically provides a way to have supervisory functions with the RTUs, and the U format, which is just a connection control functions between the SCADA and the RTU. Depending on this type, you can have either just the APCI or both the APCI and the ASDU. The ASDU itself is the part of the packet that actually contains the information regarding the power system that you are controlling. So you can have either commands or measurements in this object. Each object has a specific address identifying the specific device that is being controlled by the RTU in this case, and a single RTU may have multiple information objects associated to itself. So you can have one RTU with multiple devices, and each device will have its own information object address, and through a 104 packet, you can issue commands to all of the different devices controlled by a single RTU. Now, what you would expect of the control station connection is once you start the connection, you will follow the IEC 104 protocol requirements as is defined in the standard. When you start the TCP connection, you will enter what's known as a stop connection state in the IEC 104, which basically you have a connection with the RTU, but you're not actually issuing commands or getting data. You're just connected to it. You have to interact with it somehow before a timeout. Otherwise, the RTU will close the connection. During this time, you can actually send any U frames, which would be U format packets that will control the connection itself. You can either send what is known as the start data transfer command, which will shift the RTU from the stop connection state to the start connection state. And when you receive that, then the RTU will start reporting all the measurements to the SCADA, and the SCADA can issue commands to this RTU. This is all part of the IEC 104. And once you are in this new start connection, if you send a stop data transfer packet, then you go back again to the stop connection state, and you can remain with that same connection, or you can just close the connection with a timeout. Either way, that's the expected behavior of an RTU. So if we want to create an emulated version of this RTU, we need to follow this same procedure, and this is exactly what we did with our framework. We generated a modular component that follows this this behavior, so that if you connect to it, you can follow the same IEC 104 protocol, and it will behave the same way. So what do we want for our simulation? Obviously, we want to follow this IEC 104 standard. We must encapsulate all the data in this same protocol. We need to be able to execute any commands or simulate the execution of any commands that are sent to it. And well, obviously, we need to run everything through the actual TCP/IP sockets. That's what we want, because we want to analyze all the traffic that is exchanged between the SCADA and the RTUs. Now, when you look at a lot of the simulations that are available around, usually you have the entire system simulated as a single component, and this makes the simulation far more complicated than it has to be, from our opinion, because you will have the entire complete power grid system being simulated in a single software component, and you might miss a lot of information from what would actually happen in the real world if you do this as a whole. So our idea was, okay, let's break down this simulation into individual components, and each individual component can simulate part of the whole system, and then exchange information with all the other components, so that you can simulate the entire system in small parts. And each single individual component can be, from our perspective, a single RTU. And then you can have all the RTUs communicating with the SCADA system as you would in a real scenario. This is useful because then you can start capturing this network traffic, and you can start debugging the different packets between the different RTUs on the SCADA system, you can audit this traffic and you can compare it with real-world scenarios. Also, if you do it with individual components, this is scalable, so you can plug in new components in real time or remove components in your simulation, and the system as a whole will be able to react on that. So it makes it both scalable and more dynamic and flexible. And this is what we did. So we came up with our network emulation framework for industrial control systems. This is still a work in progress, but basically what we did was we separated the simulation into little modules, different types of RTUs, but the basic structure is the same. You have an RTU with three main components. So you have the network component, that is the component that handles all the IEC 104 related stuff. So this handles all the control station process, holds the states of that process and the timeouts, and understands the IEC 104 packets and encapsulates the data that needs to be exchanged with the SCADA, and understands the commands that are being received from the SCADA and executes these commands. These commands affect the internal status of the RTU, which basically holds all of the status information for that particular substation that is being simulated. And you have the physical component. The physical component calculates and determines the physical ramifications of the internal status of that RTU within the system. Because this is an individual component, the physical component needs to communicate with all of the other simulated RTUs in order to exchange the necessary information to simulate the system as a whole. Because if you change something in a single RTU, this change will affect all of the other RTUs as it would in a real-world system. So you need this physical component to communicate with all the other RTUs. So what we did was, okay, so we have the individual components. How do we test this? How do we make it scalable? We took advantage of Mininet, that basically is a software-defined network for prototyping stuff. And we executed our individual components in different machines in this Mininet system, along with a small SCADA application that will communicate with all the RTUs. This is a fairly low resource consumption scenario, because you have one single process, which is the Mininet, emulating different machines instead of running it on multiple machines, although you could run it on multiple machines if they are reachable via the same network. That way you can have multiple endpoints in the same simulated scenario, and you can capture that all the traffic that's being exchanged between the different RTUs and the SCADA fairly simply through the Mininet SDN switch. So this is a rather convenient environment, and we worked and developed our framework based on the premise that it would be run in this kind of scenario, although not necessarily. It can be run in real networks. So after we developed this framework, we needed to test it somehow. So inspired by the Industroyer, we came up with a proof of concept malicious software that uses the IEC 104 the same way as the Industroyer did. And the same way as the latest Industroyer known to happen, it is completely autonomous. It detects the RTUs and makes a command injection that will potentially generate a blackout in the power grid system. So a little bit of background, the Industroyer, the Ukraine case, there was a couple of attacks that happened on the power grid system. For those of you that are not familiar with this, in 2015, a compromised machine was accessed by attackers, which would then manually start messing around with the power grid and causing all sort of problems for the operators and the power grid itself. in 2016, they refined these attacks and they made this Industroyer, the malware itself, which is a lot more sophisticated. It's autonomous, so they compromise the machine, and then the attacker basically could relax and be offline while the attack happened. And then the attack will run autonomously and do pretty much the same thing we're trying to do. So how does this all work? So when we run our malicious software, we basically do an ARP scan, trying to figure out the live stations within the network. Then we do a port scan, trying to figure out whether those devices in the network are potentially RTUs if they have the proper ports open. Then we do an RTU enumeration, trying to figure out if or not they are actually an RTU. If they are an RTU, then we try to figure out if they have any breakers on them. And after we have all this enumeration, we send commands to open all the breakers in this case to generate a blackout, then disconnect from all of the different RTUs. When we run this against our NEFICS, then as far as the ARP scan, well, the underlying network actually replies with the appropriate stuff. So it worked phenomenally. The port scan, the network component of our real RTUs actually receive the incoming TCP connection. So again, it will behave as a real device. As for the RTU, if you send the appropriate IEC 104 APDU, it will reply accordingly. So if you send U frames, the test frames for the IEC 104, it will reply with the appropriate response. So it will emulate a real RTU. For the breakers, the RTUs that we made actually simulated.
Sorry to interrupt you. We are at 20 minutes. So just FYI, we're exactly at the maximum time of the presentation. Let's conclude a little bit faster. Thank you.
Okay, yeah, sure, no problem. So yeah, basically when we run the, I'll skip this then. When we executed the malware, basically you can see the replies that we get. So you can see the scanning worked, then it identified the different RTUs, then it started enumerating for each RTU the different IOAs for each breaker, and then it executed the attack for each breaker. After this, as I mentioned before, we tried to came up with a process to identify these anomalies and the behavior that this type of malware will have in the systems. So basically, we came up with a baseline scenario with normal execution of just the SCADA system and the RTUs. We captured the traffic. Then we trained an algorithm to identify the relevant features, and we came up with a clustering algorithm, basically using the k-means for those who are artificial intelligence savies out there. And then we ran the normal scenarios with the attacks, and we tried to find the appropriate clusters to establish an anomalous behavior. So these are our results for this type of defense. You can see the different clusters for the normal operation, and the operation under attack actually generated an additional cluster which indicated the anomaly. So this is another way this framework can be used. So our main idea was to have a framework that can be useful for research purposes, and we tried to emulate power grid systems as reliably as we could, following the principle that it had to support the IEC 104, which is being neglected so far. And well, while its current state is limited, we are still working on it, and we are confident that this can be a useful tool for future research in this field. Any questions?